welcome to week 16, day 1. Getting close to the end. There's this week, there's next week, and then there's finals week. There won't be a final in this class, so yay. It'll probably just be people getting caught up on all the competency exams, which will be happening a little more regularly now. Towards the end, there's only 2 programming assignments to do left. The first one, which you'll get today, is the hardest programming assignment of the semester. So you can work on it with a partner if you'd like. How many more competency exams are there? Just hash tables. That's it. And so those are the big topics: classes, linked lists, binary search trees, hash tables. I guess I can make one for stacks and queues. I don't know how to make that difficult though. Xbox Series X is in. So yeah, so basically there will be another take on some of the older ones, and then there'll be a hash table one, and call it a day. So the histogram is part 1 to the hardest assignment you're going to get this semester, and this assignment is going to make use of multiple data structures in a way that will hurt your brain and challenge you. Okay. So for this assignment, you'll have until next Wednesday to do it. I'll give you 9 days to do it. Histogram, I gave you 5 days to do it. This one, I'll give you 9 days. So histogramming is, like I said, it was about 60 lines of code. Is there a way you can redo one of the old homework for the regrading? Yeah, you have a week. If you miss an assignment, you have a week to redo it. So not the old ones, but like if you missed histogram, you have a week from today to turn it in. You have to, yeah, you can read. No, FizzBuzz. Oh Lord, no, it's way too late on that. I think over spring break, I gave you guys an opportunity to redo those, didn't I?
Yeah, you said they could redo any assignment.
Okay.
No cost.
So,
and I didn't get
that.
So
we're gonna talk about something new today. Okay, so Huffman Coding. Let me pass it here. Let me pass it, just a file name. Yeah, it takes in a number of file names. Okay. So if we have King Lear, right? So King Lear is played by Shakespeare. We word count it. You can see that it is 157,000 characters. Okay. We human readable King Lear. We can see it's 154K. So if we run the program and we pass in King Lear, then stop, Control D, we were able to compress it at a 1.6 to 1 ratio. In other words, when we write it to disk using compression, ls -lh King Lear dot encoded, it only takes up 94K. And we also are going to write something called a dictionary to disk, which is 797 bytes. And so what this assignment is, it's for, I went back through the lecture as well to see if you mention it. Yeah, should be. Okay, so we have this thing called King Lear dot dict. And what this is it holds every letter that we might want to output, and it holds which bits it's going to output when we output it. So if there's an A in King Lear, we're going to output 1, 0, 0, 1, 0, 0, 0. If we get a space, we output 1, 0, 1. If we get an exclamation mark, we're going to output 1, 1, 0, 0, 1, 0, 1, 1, 0. If we get an at, it's going to print out this long thing. And a J. Okay. So what you'll see is that characters that are more common are given less bits. So E, which is a capital E, which is, let's go down to lowercase. Lowercase e only takes up 4 bits, right? Whereas an uppercase Q is going to take up 4, 8, 12, 16 bits. Okay? So, I don't hear that either about spring break. I went back through the lectures. Yeah, did I mention it? I think I mentioned it.
Mention it during class at least. Oh, and apparently it was on modules. We're talking about the credit recovery thing for spring break, where you could do any assignment and receive. You could basically do last chance anything.
Spring break, super fun party, extra credit.
That's it.
Okay, it's not a party, but if you're missing points on any of your individual pair programming, you can redo it. Message me on Discord and we'll regrade manually. Okay. So, there you go. Alright, so what this assignment is going to do is have you guys zip a file, essentially. You guys know zip on Windows. You can compress a file or a folder down so that it's smaller on disk. That's what you're going to be doing. So you're gonna take as input a play of Shakespeare or any sort of text document, doesn't really matter, and you are going to compress it. And the way that you're going to do so is by histogramming. That's the input, so make sure you got histogram working. If not, you know, I don't know what to tell you. So you got to get histogram working. Partner with somebody that did. I don't know. That seems like maybe a good approach. And a lot of students don't have it working. Well, you know, no better time than now. Partner with somebody that did get it working. So assignments to build off each other. Yeah, of course. So you can see the most common letters like space. It's not really a letter. Character. It's just 3 bits. Whereas something like this is like, I don't know, 12, 16 bits. And the reason why this results in a smaller file size is because there's a lot more spaces than there are Qs and ampersands and things like that. So on the net balance, even though some, you know, the ASCII table is 7 bits for everything, right? By giving less bits to the common letters and more bits to the least common letters, on balance, it works out to a smaller file. And this is a provably optimal compression scheme, given certain circumstances. It's kind of like with sorting, there's ways that you can compress even further, like if there are special characteristics. You can compress better than this, but Huffman coding, given a certain set of assumptions, is actually optimal compression. Okay, so we're able to compress King Lear at a 1.6 to 1 ratio. Take it from 150 down to 90. If you only have the first half of histogram done, that should be enough for the assignment. The second half of histogramming was just trying to see if you guys could write your own sort algorithm, basically. So this is how I did it. For every letter, I made my own class. And it's got a character that is the character it is, and it's got a count, how often it is. I don't need a constructor because these things are going to construct themselves. So just whatever, empty constructor. And then I've got a less than operator. And so it compares me against somebody of the same type. If the counts are the same, then it sorts in increasing ASCII order. That's the part that got a lot of people here. You need the ASCII to go from A through Z, not Z through A, so it needs to be in increasing order. So we do that. And then we need the counts to go in decreasing order. So the highest count is first, 500, then 400, then 300. But if there's a tie, if there's multiple 300s, then the letter goes from A through Z. So the characters are sorted from A through Z, least to greatest, and the count is sorted greatest to smallest, and that was essentially the entire homework assignment right here. The rest of it is pretty easy. You just read a character at a time. Here's the whole assignment. That's it. You just say get a character at a time. If we hit the end of the file, quit. That is technically not needed. You don't need to see if it's greater than ASCII. And
Also,
so
it can't
if
be
we
less
write an
than
extended
2.
ASCII character, we just ignore it, throw it away.
Sure.
A character ranges from 0 to 127. 0 to 127 are valid ASCII characters. Negative numbers are what's called extended ASCII. Those we just throw away. We just hit continue. And then I just jump to that spot in the... I technically don't need to cast it to unsigned char. That's just an extra safety measure because I really, really hate going out of bounds. Right? So by casting it to an unsigned char, I know I can't have a negative array axis. It would work fine without it, I think. And so we jump to that spot in the histogram and increment the count by 1. And we save our character into it, which technically we don't need to do. We could have set that up elsewhere, but whatever. Okay, so we then print out the whole thing. So we iterate across the entire array and say if we saw any of that letter, then we print out the letter, casting it from unsigned char to char, which I think it's already... Oh no, that's yeah, it's an int. Right. So I could have just printed this, right? Because I have the character. I could have done count array if I wanted, because I'm saving the character. But instead, I did this just to show to you guys. Oops. So this is converting from an integer to a char. ASCII is just the number 128. So it's going to print out the letter, colon, and then the count. Do you wish to sort by count? Sure. So I make a priority queue and push all the nodes into a priority queue, and then I pop them off the priority queue. So I do a heap sort. There's other ways you can do it. I could have called sort on the array. That would have worked fine. Because I've got a less than operator defined, I could just call sort on it. So I just push all the nodes into the heap, and then I pop them off. That's it. Would have been less code to do a sort, I guess, but yeah, either way. So you did a heap sort also, the Oxlamer? I know Frisbee did heap sort as well. You don't have to. Like, you could have just been like sort. Actually, is counter array just an array? It is just an array. All right. That would work as well. So this would sort all the elements in the array. So, yeah, that would work. I think. Let's find out. Paste 4 anti equals. Let's do this. Right. It's right because it's sorting in the right. All right. If it's including all the empty. It's including all the empty ones. Okay. No, it didn't work. So, why would it not work? I'd have to debug it, but that's how it goes sometimes. I think it's sorting the count backwards. Yeah, so I probably just have to change the alligators around. That's it. Oh, right, because heaps are max heaps. Right. Yeah. So I just have to change the graders and the less thans, and it would work fine. Okay. So we are talking today, though, about Huffman coding. So how does Huffman coding work? Huffman coding works. You were printing twice. No, it was when I called sorts from least to greatest, and heap sort does max to min because it's a max heap by default. And so for my comparison operator, I would just need to change. Damn it! I deleted it. I just need to come up here and change this greater to a less and this less to a greater. It would work. That's why you see the count coming out backwards like that. See. So. Do we have a class today? Yes? I get, right? Why would there not be a class today? It's an odd question. Okay. Okay. Is it a holiday? Like April 26th? 12:18. Am I not here? Can you guys hear me? Hello? Hello? Yes. Yes, there is class right now. Because it's 12:18 now, yeah. We've been doing class for a while. I don't know. Very odd question. Okay. So I wonder if he's like in the help center or something. Panu. He's not in the voice chat, that's why. Click on the class channel. Join the voice chat. Okay. I don't know. He is in here. Okay, server mute. Huh. I don't know. Okay, so we're talking about Huffman coding. So at a high level, what Huffman coding does is do this. It figures out you first histogram. You figure out which things are more common, which letters are less common. At a big picture level, what Huffman coding does is say, okay, for the things that are really, really common, like spaces, tabs, maybe, I guess, new lines, use less bits. For things that are uncommon, use more bits. And the Huffman algorithm is the process by which you figure out how to do that. And you do so by building a tree. Okay. So all your experience working with pointers and things like that is going to come up now, because you're not building a binary search tree. You're actually going to build something called a trie. But let me show you what it looks like before we get too afraid of it. I can actually explain the algorithm like pretty quickly, I think. Actually, I have a PowerPoint presentation on this, don't I? Yeah. Why reinvent the wheel? Okay, so the reason why I want to do Huffman Coding with you guys is because it's going to require you to use multiple data structures at the same time. And when you guys were asking me like a week ago, you're like, hey, is this all there is to data structures? Or how often do I have to make my own data structure? The answer is usually the most basic things like a linked list and a hash table and a priority queue. No, I don't reinvent those. They're in the standard library. I don't reinvent them. But if you need to do like an interesting algorithm, then if you have to do an interesting algorithm, then a lot of times you have to take the basic data structures and put them together in different ways. And so for this assignment, you're going to have your histogram, which is an array or a vector or something simple like that. And you're going to build a binary tree, not a binary search tree. You're going to build a binary tree from it. And yeah, we'll go through that. But basically, you're going to have different data structures all kind of working together. So this will be a really good experience for you. Or it could be hellish, one or the other. This is honestly the hardest assignment you're going to have. So I'm going to run you guys through it. I've done some of the more annoying parts of it for you. That I'm giving you code that will do things like doing the actual encoding, the bits that you're writing. Because you have to write actual bits like 101, not as ASCII, as bits. And so you're writing like part of a character to a file, which you can't do technically because you can only write one character at a file at a minimum. And so I wrote this code that will do the bit packing and all that stuff for you, so you don't have to do that. In reality, if you're going to do this assignment, that last homework that we did with Bitfield, you would need to actually use those skills to take a 32-bit integer, and if you're given 101, you put 101 in there, and you have a count. You're like, okay, I'm now looking at bit 3. Write 111. Okay, 111 goes into the next 3, and you use the bit shifting and the bitwise ORing and stuff like that. Then you dump the int to disk and do it over and over again. You don't have to worry about that. I've done that for you. Okay. So, but this is why you both need to know how to make a data structure, and you need to know how to use the STL. So it's not like the standard template library has just replaced the need for making data structures. You're still going to need to make your own, but a lot of times you just use the STL data structures as like your building blocks. Okay. So my trigger word hard. Okay. I mean, everyone's got their own words. All right, so yeah, so like when I was looking at my compiler that I wrote as a junior in college, my compiler was a queue and a stack combined together. So tokens would come out of the queue, like int token x token equals token open parentheses token, and then that goes onto the stack. 5 goes onto the stack plus 3 plus close parentheses pop 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 8. So integer x equals 8. And so I had a queue and a stack kind of working together. Every open curly brace, every open parentheses pushes things onto the stack. The queue is the file that's basically being read in. If you think about how undo and redo work, these are pairs of stacks. So when you undo and redo, it's popping off one stack and pushing on the other. And then when you do a new command, the redo stack vanishes. So if you hit undo, 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 redo, 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 they're popping off one stack and going onto the other one. But as soon as you do something, the redo stack vanishes and it starts adding up new commands onto the undo stack. Printer just came alive. It just printed something. Blank sheet of paper with just an arrow on it. I know what you did last summer. Alright. Right, or so like when we did the hash table thing, I made my own hash table by combining a vector with a binary search trees. In this case, I say an array with a linked list, either way. Okay, so anyway, yeah, so the point is the possibilities are endless. And and as you advance in computer science, the reason why you have to take this class is to get that sort of basic, fundamental skill with data structures, like, inserting, searching, deleting, and then you can sort of step back and zoom out of it. And you're just like, okay, I just have a hash table, and the hash table is going to hold, how often a word appears in a file or something like that. Zoom out. You don't have to worry about like all the modulusing and going to the next and stuff like that. You've got a hash table class. You just zoom out. You toss words in there, and every time the word appears, you update the count. Boom. Handled for you. Half the man he used to be. Stone Temple Pilots song. Right? Yeah. Okay. Once you develop an understanding of which data structures are right for which jobs, you'll have an intuition of how to use them, right? And so one of the signs of like a new programmer is that they like try doing everything from scratch. And because they don't know exactly what's been done for them and what tools are available for them and what parts of the standard library they should be using, things like that. So that's one of the reasons why in this class we've been sort of systematically going through the standard library, just so you know what's in there, and then you don't have to reinvent the wheel. Common tasks typically have a function for you, right? If you want to find the smallest element in an array, there's a function for that, right? We've gone through CPP reference before and just talked about this stuff, right? Have we? It's Creep by Stone Temple Pilots. My printer is being creepy. I don't know. A little bit? Okay. So here's CPP reference. Let's zoom in a little bit so you can read it. So this is sort of, it's good to know what's in the standard library, right? Localizations is used if you're going to support multiple languages. Familiarize yourself with the localizations library. Okay. Atomic operations are useful if atomic operations can't be split in half. It's like, what does that mean? It's like if you have two threads that are reading and writing to a file. If you could start reading to a file, or start writing to a file, and this guy starts writing to the file, is it going to intermix the two outputs and completely destroy your file? Atomic operations cannot be split. That's why they're called atoms. Atoms can't be split. So, yeah, atomic operations, either they take place or they don't take place. So if you have two threads trying to do an atomic operation, it'll either do X first, then Y, or it'll do Y first, then X. They won't intermix and split everything. So if you're going to be doing threads, parallel processing, you can have multiple threads doing different things at the same time. Then you should also learn about atomic operations. You should also learn about mutexes. Mutexes are, if you have non-atomic operations, if you've got thread A writing to a file and thread B writing to a file, thread A can acquire a lock on the file and write to it. When it's done, it releases the lock, and then thread B acquires the lock, writes to the file, releases the lock. Really important stuff. We don't need to know it right now. Containers, this is what we've been talking about this semester. Okay, nuclear Gandhi. Right. So this semester we've really been learning the basic containers in C++. We haven't learned span. Span is new in C++ 20. And yeah, and it's, yeah, we can talk about that some other time. But vector, map is binary search tree. Unordered map is hash table. Priority queue is heap. And then where is list? Okay, click on containers library. List is a doubly linked list, forward list, singly linked list, and a deck. So these are your basic containers, right? And you guys know all of them now, except for span. Span's not really that hard to learn. Yeah, we should talk about it at some point, but it doesn't matter right now. You guys know all of these, right? You know what an array is, you know what a vector is, you know what a deck is, you know what a singly and doubly linked list are. Binary search tree, Also binary search tree, but this is a... Remember how we talked about key and values? You know, with a set, the key is the value. With a map, you can have a separate key and value pair. So you can associate between strings and integers to count how many times the string appears in a file. This allows duplicates. This allows duplicates. So this is binary search tree. All these are binary search trees, just 4 different flavors of them. Do they allow duplicates or not? Is the key the value, or do you have a separate key and value? And then these are hash tables. And then these are stacks, queues, and heaps. So that's it. You guys know the entire standard library of containers now in one semester. Okay. If you don't know any of these, please ask. Like if you're not sure what the difference is between a forward list and a list, just ask. But these are your basic building blocks of all complicated assignments. Talked about smart pointers last week. We've talked about pairs and tuples before. Optional, any, and variant are important. We should maybe cover them, maybe not. I don't know. Concepts is some new hotness that's pretty neat. Ranges and iterators we've talked about in conjunction with the containers. Strings, you guys know strings. Numerics library. So absolute value, modulus, max, min, exponentiation, e to the x, 2 to the x, logarithm, log base 10, log base 2, exponentiation, general exponentiation, square root, cubic root, hypot, which is Pythagorean theorem that we use a lot. I use hypot all the time. Sine, cosine, cotangent, all the different trigonometric functions you could ever want. Gamma function, I don't know what that is. I assume it has something to do with the Hulk, right? He was exposed to a gamma function and became the Hulk, something like that. I don't know. Not really a math person. Natural log, I don't know what that is either. Confused about virtual functions with inheritance. So if you're going to do inheritance, you need to mark in the superclass, in the parent class, any function that you want the child class to be able to override. You have to mark them as virtual. Otherwise, bad things will happen to you. So just as a general principle, if you're making a class hierarchy with A as the parent, B and C as the kids, mark every function in A as virtual. There's a small performance penalty, which is why it's not just automatic. In Java, it's automatic. In C++, it's not. You have to mark them as virtual. So if you're going to be doing inheritance, mark everything as virtual and call it a day. Then things will just work the way they're supposed to. Rounding to the nearest function, rounding up, rounding down, all sorts of variants of these things. So there's a ton of mathematical... I don't know what any of these things are. Cylindrical... Oh, of course. You know what the cylindrical Bessel function is, right? The irregular modified cylindrical... Why is this in the standard library? I don't know. I mean, I guess I get it, but... Yeah. But it's only the first kind, right? We don't have the second kind of cylindrical Bessel functions. Computes... The Wikipedia link? Yeah, it's a Wikipedia link. There you go. Plot of the Bessel function of the first kind. There you go. What is the Bessel function of the second kind? There we go. There's the Bessel function of the second kind. Yeah. Elliptic integral of the second kind. I don't know. A lot of advanced math stuff that spherical Neumann function. I don't know. Can't help you. I can't help you with that. Math constants. Oh yeah, this is kind of useful. So if you want to pi log base 2, log base 10, square root of 2, there's constants for those. You don't have to type them yourself. It's kind of useful, I guess. Well, it is useful, I should say. So, That's actually kind of cool. Yeah, we should talk about that sometime. Oh. Greatest common divisor, least common multiple, lerping. I can't believe this was C++ 20. How do we have like irregular Bessel functions, right? And we don't have lerp, right? Like until now. And so lerp will, if you have point A and point B and you say what percentage you are between point A and point B, it will linear interpolate between that point. So very useful. I use lerp all the damn time. I don't know why that is C++ 20. We got Bessel functions of the first kind. You know, not lerping. GCD, iota fills an array with numbers like 1, 2, 3, 4, 5, 6, 7. Pretty basic stuff. You don't really need to know it. You can do it yourself if you want to. Accumulate is also something you can do yourself. But if you want to add up all the values in a data structure, you can just call accumulate on it. So if you, nobody used this for the linked list. Linked list, was it take 3 or something like that, where you had to add up all the values in a linked list, but you could have. Accumulate, list.begin, list.end. It's dot product, right? Basically. Random number generation, that's really important. So we typically use MTT19939, which is absurd, but yeah, the random number library in C++ is really over-engineered. It's way more complicated than it needs to be, but I think I've given you guys code on how to do code with that, and it's got all sorts of different distributions and things like that. I typically only use uniform int distribution and occasionally actually pretty much only that. So this shows you how you can generate random numbers and stuff like that. The library name is random. Hashtag include random. CPP reference is the website. So yeah, just going through that and just kind of seeing what's there. Like, you don't even have to like understand random. Just know that random exists is usually good enough, right? So if you're called upon to make a random number, then yeah, sure, you can use the old C stuff, rand and srand, but just knowing that there's a better alternative in C++, better in the sense that it makes better random numbers, worse in the sense that it's way more verbose and hard to understand. But just knowing that it's there, you can click on this and then you can look at the sample source code, go down to the bottom, and you can see how to make a random number from 1 to 6, right, or whatever. So CPP standard library added e to the negative t times t to the x minus 1th power dt before they added lerp. Yeah. Okay. So there's all sorts of stuff in the numerics library. The algorithms library, where are you? There you go. The algorithms library has a bunch of stuff that runs on ranges. So if I give you a range, vec.begin, vec.end, or nowadays you can, C++ 20, it's still kind of coming online, so don't rely on it quite yet. You can just say sort vec, which is nice. For each element in a range, find, we've been using find, right, to search for an element within a data structure. Count how many times an element appears in a data structure. For each element in a data structure, do something. This is very similar to the range-based for loop, right? So I don't typically use it. But you could say for each character in the string, do something. It's more or less the same you could do with a range-based for loop. Copy. So you can copy from one data structure to another. Move. We talked about move before. So that will actually steal the elements from one vector and put it into another vector. So the old vector has been invalidated. Like, it actually rips its guts out and puts it into the new one. We typically do that if we're going to like pass a unique pointer. So like if you have a unique pointer, you can't copy it. So you can't pass a unique pointer to a function, but you can move it. If you rip the internal guts out and pass it, now that new person is the owner of of that memory. Fill will fill an array with data. So if you want to zero fill an array, you can say fill vec.begin, vec.end 0, and that'll fill the vector with zeros if you want. Yeah. So these are all the kinds of things. Shuffle, random shuffle all the elements in an array. Unique will delete duplicates out of an array. So there's, sort. It's classic sort. Merge. We'll put two different. If you have two different sorted vectors, you can merge them into a sorted vector and order in time, which is nice. Yeah, there's a lot of things. There's a lot of things in there, and just kind of over time, you'll develop more of a understanding of what exists, and then you don't have to redo everything. It's really nice. Complex numbers exist already. So that assignment where you had to make your own complex numbers, you didn't need to. In real life, you don't. There's one already, right? There is already a complex number class in the standard library. You don't need to make your own. And they have overloaded addition, subtraction, multiplication, division, comparison, outputting, inputting, adding, gets the real part, gets the imaginary part, exponentiation, logarithm. Yeah. So there's a much better version in there. So yeah, so that's part of growing up. Like, you guys actually know everything there is to know in computer science as far as like the basics of the language, right? You guys know how to make variables, you know how to do if statements, you know how to do a for loop, and you know how to make a function, you know how to make a class, you know how to do IO. That's it. That's all there is ever. Algebra, that's all there is. Like, when you get to grad school, you don't learn like some secret way of doing algebra. No, you guys know it all already. Like, you guys know everything there is in computer science. Like, there's only 6 tools we ever use. But in order to grow, in order to solve more and more complicated problems, you have to be able to step back, right, and abstract, right? And so rather than getting lost in the weeds and like having to make your own hash table and stuff like that, you're like, I'm just going to use a hash table. You can like zoom out a level, right? You don't even know what you know. I know what you know. The making a variable, input, output, algebra, functions, if statements, loops, classes. Yeah. That's what you know. That's what you know. That's all there is in computer science. So in order to make a really big, complicated program like Windows or Microsoft Office or World of Warcraft or something like that, you don't just start with like Notepad and start coding. Like, what you do is you think about all the different pieces that need to exist, and you make a class for them, and the classes have interfaces, and then you zoom out a level, and then you say, okay, this guy is going to talk to these different things. You zoom out a level. And yeah, architecting something like Windows is just to even look at the class hierarchy for it is like enormously complicated. But you start small, you make little pieces that work, and you plug those pieces together into bigger and bigger things until you have a working thing. And that's what Huffman Coding is going to teach you. Okay. So we are going to combine a binary tree with a priority queue and that array. So we're going to have a binary tree, not a binary search tree, binary tree. We're going to have a priority queue, a heap, and we're going to have that histogram array as kind of input into it. Okay. And so it sounds scary, but once you kind of understand how it works, it's not too bad. Okay. Are you guys ready to learn how Huffman Coding works? We've been given the Legos to master the way it's building. Yeah, exactly. Like, or like in music, right? Like, when you start off with music, you like play individual notes. Play a C. Nope, wrong note. Play a C. Okay, you got it. Play a D. No, not wrong. Play a D. When you start off, you're just trying to play individual notes, right? But then when you get better at music, you start thinking of at a higher level, right? Like a musical phrase, right? And then you're going to put phrases together to make sentence musically. I don't know. If you're not a musician, it probably doesn't make any sense to you. Right? And so you start off just zeroing in on individual notes when you're playing music, and then when you get better at it, you start zooming out a little bit. Like, oh, that phrase is like this phrase, except it ends on a down note instead of an up note to give resolution. Okay. And if you talk to music people, when they talk to each other, they're like, yes, this song is very open. And so they did an inversion of the third chord in order to give it more of a... And I'm just sitting there like, okay. Because I'm not very much of a music person. You know, I try to learn, but I'm really not very good at it. But like I'll hang out with like Max, the music instructor on campus, and he's a smart dude and he knows his stuff, and it's always fun talking to him, and I understand half of the words that he's saying. You know, but like that's do you guys understand what I mean? Like he's not saying first he played a C, then he played an A and a C together. No, he's like, you know, they zoom out, right? Zoom out. Okay. How does a binary tree differ from a trie? All right, we're about to learn. Start a class next week. Now I'm going to give you an extra 2 days on this, okay? And I'm going to make this a 20-point assignment, okay? So I want you guys to not be like, oh, it's hard. I'm just not going to do it. So it's worth 20 points, okay? So prove yourself. Take on the challenge. Pick up the Olympic torch and run it to the finish line or something. I don't know. Okay. So the program is just going to take a file name, or multiple file names. It doesn't really matter. And it's going to compress each of the files that are passed in. That's it. So like you saw, I typed in King Lear, it compressed it, then I hit Control D. Control D is end of file, right, to end the program. Make it a double. Yeah. Yoxtimer, what did you say wow for? Yeah, we're going to go over tries in a second. Okay. So I'll give you 2 extra days. Yeah. I want you guys to do this. So the first step is what you've already done, hopefully. If you didn't do it, you got to do it. You got to start off by counting how many times each letter appears. Okay? So there's 4 lowercase a's, 3 lowercase b's, and 1 uppercase a. So you then sort it by count. Hey, you've already done that. Hopefully you've already done that. So you sort it by count. So A is the most common, capital A. Lowercase a is the most common. Capital A is the least common. Okay. That's what you've done. Or should have done. Hopefully you've done it. If you haven't done it, you're going to need to do it anyway, so sucks for you. Can we use the WinZip plugin? No, because we're not doing zip compression. Zip compression is different. This is I just use that as an analogy. We're not actually using zip. So a trie is a tree. Let's see if I can hide the webcam here. There we go. A trie is a binary tree. A trie is a binary tree where the position on the tree is actually the it actually really matters where you are on the tree. Okay. So let me show you a picture. So here we have okay. So here we have a trie. And every node, in this case, is not a binary tree or a binary trie. It's actually every node can have 26 kids, 1 for each letter. Okay, so root doesn't represent anything. And it's got 26 kids, 1 for A, 1 for I, 1 for T, and the other ones don't have any, they're all null pointers for everything else. And the kid for T has a kid for O and a kid for E. And the kid for TE has A and D and N. And this guy, I and N. So the position in the trie is the data being held. So we actually don't store TED anywhere. Like the word TED does not appear in the trie. All that we have is a binary, no, it's not a binary tree, it's a tree. It's a tree that has the teeth kid exists, the eth kid exists of T, and the deeth kid exists of E. And as you traverse down the tree, the way you go down, T to E to D, is the string TED. And this in and of itself can actually compress very well, because a lot of the English language is redundant, right? We have a lot of words that begin with cat, right? Catapult, cataphract, catastrophe, right? And so tries are actually used for like predictive text, right? So when you have your cell phone open and you type in TE, so I wonder what it'll do. Go on to Discord here, chat channel for 41. Did you do a Zybooks on this? I think so. It'll probably help if you did the Zybooks. So if I type in TES, then it will autocomplete to test. Okay. So the try, a lot of times they'll hold the count, how often. If you're here, if you've typed in T and E, the most probable letter coming after that is S. And after S, the most probable letter is T. And it came up with both test and testing. And so the try can hold the entire English dictionary in one data structure with basically a count of which, whatever you've typed in, A, B, O, let's see what that does. If I type in A, B, O, then it predicts about, right? So, because that's the most likely word that follows A, B, and O. But you don't have to hold these letters over and over again. You only have to have one node for TE, the substring TE, right? So rather than storing the dictionary in this big, massive file, which is like 100K or so, if you store it in a try, a lot of times it's actually much smaller to hold it that way. So, so what we're going to do is we're going to build a try. And oftentimes, which ones are actually words? Like N is a word, right? There will usually be like a binary bit or something that says this is actually a word. So the deth kid and the oath kid tagged, yeah, that's actually a valid word. But DO is a word, DOL is not a word, but DOLL is a word. DORK is a word, DORM is a word. Do you guys understand? Like, if you've done the Zybooks, you probably know this already. Yes? So imagine for this try, you've got 26 kids at every node, and you have a null pointer. You have pointers to other nodes. They're null if there's no such kid. Like S to Z is going to be a null pointer. We're only drawing the links that exist. So S is a pointer to this node that represents E. He's got a pointer to this code which represents N. And so the position that a node is in the tree is its value. Okay, so the Huffman coding is going to be using a try, but it's not going to be using this try. It's going to be doing a binary try. So it's going to be a binary tree, and I'll go over how we build that in just a second. So here are the steps to Huffman coding. First step, histogram it. Done. Hopefully. Done. In this example, how would you know what to mark as word? Let's say that we were... So let's say that we're opening up the entire English dictionary, which exists, by the way. So in Unix, there is a file that holds every word in the English language, and if you're like, how do you know what every word in the English language is? There's different dictionaries, and so you can actually install a different dictionary depending on the needs. The default one is user shared dict words. There's also a small dict, a big dict, an extra large dict, and a medium dict. And you can actually choose which one of them is the official dictionary for your system. And I think I have the large one turned on. I don't actually remember off the top of my head. Let's see. ls-l. American, so it's just the default American English one. cd user share dict. cd words. No, I can't. So, yeah, there are other packages you can install that will install different size dictionaries and things like that. I'm just using the default. It seems to work well enough. So anyway, so when you're going through the dictionary, when you get to the end of the word, like you would insert these into the try over and over again. When you're building that try, you would go through the dictionary and insert zoom. And so it'll start off by saying, does the root node have a Z? No? Make one. Go to the Z one. Go to the oath pointer. O is A, B, C, D, the 15th. So for every node, there's going to be an array of 26 pointers that are null by default. O is the 15th pointer. It's null currently. So we will create a new node, go to it, and its oath pointer, ZOOM, is also null, so we make another node. Does it have an M pointer? Nope, make it, and we're done. And we tag that node as being a correct word. And then when we come through another time, Z exists, O exists, O exists, M exists, but its hyphen character does not exist, so we create one for that. And then we create a child for the S, and then we tag that as being a complete word, and we return. And so each one of these things, when we get to the last character, there's a binary bit that we set saying this is actually a word. And so when you're doing text prediction, if the user types in ZOO, it'll go through and say, okay, there's two possibilities from here. There's M and there's S. And so if you're doing like, predictive text on your cell phone, you types in ZOO, it'll be like, do you want to type in Zoom or do you wish to type in zoos or zoo? Actually, zoo is a word also, so maybe zoo would come up also. Okay. And so, yeah. What about with those extended ASCII characters? I don't remember off the top of my head whether we're handling those or not. I don't think we are. Okay, maybe we are. I don't know. I'd have to look. So, yeah, so step 1, you histogram your homework assignment. Step 2 is you sort it by count, which you guys have done. Okay, step 3. Well, it's kind of what I did in my histogram assignment. I had a node class, so every node has a character and a count, and a less than operator defined. Yes, but it's gonna have a pointer to left and right, kids. So this is what you saw, the first 3 things here. But you're going to create a node class that has a pointer to 2 other nodes. And this is going to be the try. And the try is going to look like this. Actually, let me just show you how we... Let me just actually fire up one node. I can walk you through. Did I mess anything up if you didn't use heap sort? No. Any way that you can sort it is fine. Let me just show you how this is built. It might be easier that way. So let's say that you've got 4 letters in the file. Let's just make it easy. There's A that has a count of 10. There's B that has a count of 5. There's C that has a count of 2. And there's Q that has a count of 1. Okay. So here's the algorithm for Huffman coding. You guys ready? Nothing? People's brains are dead already? Hope not, because we're coming to the important part here. Everybody type when you're ready. This is the important part. Everything we talked about so far is just background. All right. By now we did the count. You know how many you have. Yes, you know the letter, you know the count of the letter, and they're sorted by count. Okay? So, here's the algorithm. Step 1. Pop to smallest. Who are the two smallest? C and Q. You ever did ham radio? Those are letters of special significance. This is KC6KSB calling CQ. Is anyone out there? Please come in. I did ham radio for a while. That was my call sign. KC6KSB. Not done that in a long time, though. Okay, so we pop these two guys off. Boom, boom. They're out. We create a node for them. C, the count of 2. Q, the count of 2. Make nodes for them. And then we push their sum onto the heap. What does that mean? Well, we make a new entry that is their sum. It doesn't have a letter because it's not a, doesn't correspond to anything in particular. And its sum is 3. Q is 1. Yes, you're right. Thank you. 1. Okay. Repeat until empty. That's the algorithm. What? One other thing. For the sum here, we set its kids to be the ones the nodes just created. Okay. Repeat until the queue is empty, until the priority queue is empty. That's the algorithm. So you're going to pop the two people off the priority queue, and you're going to push a new node for the sum onto the priority queue. So, repeat. What are the two smallest ones on the priority queue now? What are the two smallest entries in the priority queue now? Yep. B and 3, I guess we can call it. I don't know. So these guys get popped off. We make a node for B with a count of 3 and 5. Sorry, count of 5, and then we push the sum on. So the sum comes on with a sum of 8. Okay, what's next? Step 2, make nodes. So you pop them off, you make nodes for the two things, if they don't exist already, and kind of link everything up like that. And then you push the result back onto the stack, or onto the heap, sorry. So what's next? Who are the two smallest people now? 8. A and blank, all right. And now the priority queue is empty, so we're done. So room. Yep. Okay. So then A is going to be created. It doesn't matter. It actually doesn't matter if I put A on the left or the right side. It actually doesn't matter. I'll just draw it here for simplicity's sake. A is here with a count of, what was it, 8? No, what was it? I forget. What was the count? 10. Okay. All right. And then we create a new node, and this is going to be the root because it's the last one with a count of 18. And that's it. So that is Huffman coding. If you can do that, the assignment's basically done. So you start off with a list of all of the characters and their counts, and repeatedly over and over again, you pop the two smallest ones off, and you push an intermediate node with their total count back into the priority queue. In this case, we kind of just went right to left, but we'll do another example that sometimes the intermediate nodes are, the biggest or whatever. It really doesn't matter. It's just you repeat that process over and over again until the priority queue is empty, or technically there's one. If you push this on, there's one thing left, and you can't pop two off, and you're done. Okay. So that is Huffman coding. You're like, wait, what? How did I compress anything? I thought we were doing file compression. Yeah. Well, let me show you. Let me show you how this translates into file compression. This is a trie, and it is a binary trie, and so the value that these things are going to encode to is based on their position in the tree. A left child is a 0-bit, a right child is a 1-bit. So A is going to encode to 1. Intermediate nodes don't encode to anything because they don't represent any character. So B will encode to 0, 1. C will encode to 0, 0, 0. And Q will encode to what? What will Q encode to? It's not a 2. It's a 0. So what will Q encode to? 0, 0, 1. Yeah. And then you just dump that. That's the dictionary file. That's it. So you just say, all right, A, is A, like the dictionary file that I showed you guys earlier. We've already seen King Lear. Let's look at a different. Let's look at Hamlet's dictionary file. So, lowercase a. So lowercase a is going to encode to 0010. Lowercase e is going to encode to 1100. Okay. And so these are just the positions in the tree. And so A was the left child. You go left, you go left, you go right, you go left. And that's A. Okay. H is 1, 1, 1, 0, 1. So this is the position in the tree that the leaves were in. And that's it. This is actually a provably optimal compression algorithm. That's it. That's the whole thing. You guys got 9 days to do that with a partner. And it'll be tricky because you're going to have to, have a data structure that will hold the character, the count, the character encoding. You're going to be newing things and having pointers pointing at these things that are newed and things like that. But basically, this is a tree you actually build from the leaves upwards. So when you push this thing back into the data structure, I'm actually pushing a pointer to this thing in here. And so you can actually start off by just making a node for each of the leaves. And then having inside of here like a pointer, like you have some data structure, like the node class that I showed you earlier. And it could have the encoding, it can hold the character, it can hold the count, like 2 or whatever, and it can hold a pointer, which is where it is in this trie that's being built. And so when you pop the two things off, you just basically create a new node. Its left pointer is one of them, its right pointer is the other one. At the end of the day, you're going to end up, and these things build upwards. It's a tree that builds upwards. And you're going to end up with a root pointer here, and then you're going to go through the root pointer and basically, do you guys remember how to recursively traverse a tree? Like print tree, or whatever? Except what you're going to do is you're going to like go to the left, go to the left, go to the left. Ah, that's a leaf. Okay, well, your encoding, sir, is left, 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 0, 0, 0. And return, go to the right. Okay, your encoding is 0, 0, 1, right? And so after you build the tree, you're going to recursively traverse the tree and give each character its encoding. And that's it. Then you're going to basically print that to that dictionary file like this. And then you're actually going to compress the file, and I've done that for you. I've done the code that will actually do the, it's called binary writer. That. And so basically, you just pass in, like if you're going to write 101, you just pass 101 to it, and it does all the bit shifting and things like that into it. And when the thing closes, this is all the bit shifting magic that I was telling you about. And so this actually does all the bit packing for you and things like that. So yeah. So I've given you the class that will actually write the compressed version to disk. If like much ado about nothing. Do I not have a copy of that? All right. Find name. Much ado. Okay. So much ado gets compressed at a 1.6 ratio also. So so much ado about nothing was originally 121K, and after being compressed, should be encoded, is 74K, and the dictionary, the dict file is 790 bytes. So you can see we smashed the file down quite nicely. After you convert the characters to bits, combine all the bits into a string matching said characters. Yes. So then you actually are going to compress much ado about nothing by basically just repeatedly looking up the characters in the try, right? If much ado about nothing says print E, then you send to my binary writer the encoding of E, which is 1101. You just do a lookup over and over again, passing it over to the binary writer, and the binary writer is what actually compresses the file down. You basically pass it the ones and zeros. And so you're going to read one character at a time from the file, look up its encoding in that data structure you created, and pass the encoding to the binary writer, and the binary writer is going to spit the bits out. Would you guys like to see another example of this? Okay. So let's compress assist. Okay. How would this compress using Huffman coding? All right, we'll start off by making structure. So this is the character, this is the count, and then later on we'll have the encoding and the pointer, but not just yet. Okay, so we're going to start off by doing a histogram. How many times does capital A appear? We're taking it back to basics. How many times does capital A appear? 1. How many times does lowercase s appear? 3. Lowercase I, 1. T, 1. Maybe it's not the best word. I don't know. Okay, so we sort it. This is, again, the homework you've already done. You're going to sort this by count. And I think the secondary sort by ASCII actually doesn't matter. Maybe. I don't know. So S, A, 3, 1. Okay. Now, I would start off by making a node for each of these. So S, A, I, N, T, S, A, I, N, T. I'd start off by just making a node for each of these. New them, write down their, this. I just hold into this data structure where they are, like that. I'm going to erase those so they don't get in the way. Okay, let's do Huffman. So this was what we've done so far was your previous homework assignment. Now we're going to do Huffman. So, pop. This is the rule. Pop the two smallest counts off, and then push an intermediate node into the priority queue. That has a count of the sum of the two leaves, of the two things that you just popped. So what are the two smallest things on here? We have three smalls, yeah, but the heap doesn't care. Hello?
Good afternoon. This is Matt calling from Business Connection Group. Well, I just have an information to send out in regards to your upcoming office move.
INT. Yeah. The IT guys. So we're going to pop INT off the heap. And these guys are going to pop off. And count of three. Or sorry, count of. It's got a count of one, and then we're going to push an intermediate node on here that has a count of 2. Okay, but now this is not in order, right? So it's a heap, so it's always sorted, right? Heaps are always sorted. So now it looks like this. Okay. Now we pop the two smallest off and push an intermediate node back on. Which two are the smallest now? Maybe I should have picked a slightly bigger word. Oh. Blank and A, right? So these two guys pop off the queue. And we're going to put a 3 back on. So the A and the 2 pop off, and we push a 3 back on. That's it. 1 also. And then we are going to pop the S and the blank off. We get 1 with 6, and we're done. So this is, and maybe I should have picked a slightly bigger one. Oh. So the encoding is going to be, so S is going to encode to 0. Sorry, S encodes to 0. So back up in here. We're going to have a separate heap than this. This is we're going to have like a master table of all the different letters. So probably shouldn't have been popping out of this thing, but we would actually have a separate heap for this. I and T, so this is a count of 1, 1, 1. So the encoding of S would be 0. Encoding of S is 0. The encoding for A is 1, 0. The encoding for I would be 1, 1, 0. The encoding for T would be 1, 1, 1. So, if we were to encode assist into binary using Huffman coding, this would encode as, what is A? If we're actually talking about bits now. What encoding does A have? What's the binary encoding for A? What if the blank was higher than the S? Yeah, we'll have to do another example because these have been a little bit too simple. 1, 0, okay. And then S encodes to what? Or done the wrong encoding again. S encodes to 0. So it's going to be 1, 0, then S, then I encodes to 1, 1, 0. S is another 0. And T encodes to 1, 1, 1. So before, this would have been 1, 2, 3, 4, 5, 6. So before, it would be 6 bytes, which is 48 bits. After, this would be 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. So if we were to Huffman encode assist, this would compress it at about a 4-to-1 ratio. So because we're only using 1 bit for S instead of 8. So that's kind of the maximum you can get is 8-to-1, I guess, if everything's an S. parcel tongue. Get 8-to-1 encoding. So do you guys see that? So this is the final step, right? Is you take King Lear or whatever, and you just look up in the table. A's encoding is 10, so we output a 10, 1, 0. S's encoding is 0, so we output a 0. S's encoding is 0, so we output a 0. I's encoding is 1, 1, 0, so we output 1, 1, 0.
Yeah, why is the bagel sandwich you got me pink?
That's tomato aioli.
And why is it sweet?
It's, I don't know, a thing. Oh, it's the bagel. The bagel itself is a mixed berry bagel. I thought it would be an interesting combination of sweet and savory for such a sweet daughter as yourself. So it's a mixed berry bagel with bacon and eggs and tomato aioli on it. Mmm, delicious.
Okay.
Do you not like it? You can have half my sandwich. It's a different
That's okay.
breakfast sandwich. So you guys see that? Do you want one more example? Maybe something a little bit longer, so we get a little. Because so far this tree building process has been pretty basic. All right, somebody give me I don't know. More examples. Code-wise, you're gonna have like a table, like that table that you have right now for your histogram. It's gonna have the character you have, the count. You're just gonna add 2 more entries. One is the encoding, which gets figured out at the very end of this process, and you'll have a pointer where it lives. Right? And then you might even want to do this using a hash table, maybe, for extra speed. Yellow dog walked to the grocery and ate a pineapple. Supercalifragilisticexpialidocious. The quick brown fox jumped over the lazy dog. And so the pointers would be just like that. I'm not going to draw them because it's going to put too much ink on the table. So I would start off by just newing. I would make a node for each of those people. And then when you're trying to look them up, it'll look up the pointer, and then you can build the trie out of that. Like I said, there's multiple data structures going on. You got your histogram. You're gonna have a priority queue that's kind of sorting all of these things, and things are gonna be coming off the priority queue. You want a min queue, so the smallest things are coming off the queue first, and you're gonna look up in this table here of all your stuff where the nodes are on the tree, and the tree is gonna grow from the roots up. So there's 3 different data structures you're gonna need to be handling. Okay, let's do assist the students. So that, hopefully, we got 2 E's, we got 4 T's. Yeah, hopefully this will be a little more interesting. Okay. So we're going to have some sort of like hash table or something like that. All right, so 1, 2, 3, 4, 5 S's. I think that's the most. So that's the character, that's the count. Count is 5. T, 1, 2, 3, 4 T's. 1 E, 2 E's, 1 I. The rest are solitaries. Okay. Let's see how this goes. Okay, so capital A has 1. E, sorry, it's Japanese E. I, 1. H is 1. D is 1. U is 1. N is 1. Okay. Did I get them all? Am I forgetting letters? D, N, E, Yeah. E, it's 2. Squeeze that one in there. All right, there's 2 E's. Thank you. All right. All right, so I'd start off by just making a node for each one of those. And then using the priority queue to control which 2 should be processed first. So in this case, U and N are going to get processed first. I'll just mark, because I'm not really deleting them out of the master registry, right? I don't know, like they're processed, like maybe a Boolean or something like that. I don't know. Just show they're not in the priority queue anymore. So we'll start off with U and N. They have a count of 1 each, so this intermediate node has a count of 2. And we can even call this guy UN just so it has a name for it, if you like. You can call this one UN, United Nations. There we go. So you don't have to constantly just call it blank, you know. Okay, so we pop those guys off. We push on to the priority queue UN, which will, I don't want to erase the whole thing. UN count of 2 is going to be like up in here somewhere. So we pop 2 more people off the priority queue. H and D get popped off. So they're not attached to this one yet. We have H, we have D. They are not attached. You're actually growing a forest of trees. So high def with a count of 2 is there. This tree is going to grow from the leaves to the root, and they're going to start off disconnected. They're going to start off with every node disconnected, and they're going to eventually connect together. So H and D have been processed, and then the node for HD is going to, because I don't want to erase everything, HD with it's going to be up in there too. Now we're going to process capital A, lowercase I. So artificial intelligence, A and I. We're going to make a new node for artificial intelligence with a size of 2 also. So these guys have been processed. And AI is also going to be up in this spot right around there. I don't want to erase and redraw. Okay, so now we've got E, we've got AI, we've got UN, we got HD. So I guess, I don't know, just the way I drew it, UN and HD are the least. It doesn't actually matter. In the case of a tie, it doesn't matter. So we're going to add the HDUN node with a size of 4. So these guys get popped off, and HDUN with a size of 4 is going to come up into here. And then we're going to pop off E and AI. So E has a size of 4. It's going to hook up to AI, and we're going to have AIE with a size of 4 as well. E has a size of 2, of course. I've run out of room. That's why it's easier to do on a whiteboard, but whatever. Okay, so we've processed AI. We've processed AI. We've processed E. So all there is left are HDUN. Oh, and we have to add AIE in here as well. AIE with a size of 4. Let's go up in there as well. Okay, so just the way that I've drawn it, T and AIE are the smallest ones now. So T is going to pop off. AIE is going to pop off. We push on T with a size of 4. We're going to push AIE and T with a size of 8 on there. Then HDUN and S are now the new smallest, because 8 with a size of 8 is bigger than all of these guys. So we've got S with a size of 5 and HDUN with a size of 4. So these guys are going to pop off. So S with a size of 5, HDUN with a size of 4 is going to form HDUNS with a size of 9. Then finally, the last 2 elements are IT and HDUNS, and I've run out of room again, so I'm just going to squeeze this in here. I'm just going to call that the root, size of 17. Okay, so now we've built the tree. We're done, and then we're going to recursively go through the tree and just give everybody an encoding based on its position in the tree. So you are 0. Everybody to the left is a 0. Everybody to the right is a 1. So A is going to encode to 0, 0, 0, 0. I is going to encode to 0, 0, 0, 1. E is going to encode to 0, 0, 1. I guess I can write these up here. So the encoding. The encoding of A is 0, 0, 0, 0. You see that? To the left, to the left, to the left, to the left. His position in the tree. I is left, 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 right. So 0, 0, 0, 1. H is 1, 0, 0, 0. D is 1, 0, 0, 1. U is 1, 0, 1, 0. N is 1, 0, 1, 1. E is 0, 0, 1. T is 0, 1. 0, 1 is T. And S is 1, 1. Okay. So what about spaces? Now you ask about the spaces. Damn it. We would have to rerun the whole algorithm. And I'm not going to do it. So. Yeah, spaces should have been in there. But too late now. Okay. So it's assist students, all one word. Ass is the students. Wait. Go. Don't worry if this looks confusing. The core thing to remember is the building of the tree is the hard part. It's not even that hard, really. You just sort everybody by count. You're always taking the two smallest counts off and then adding them to a tree. You have to set the pointers. And then the result goes back onto the priority queue. That's Huffman coding. Pop the two smallest. My phone keeps blowing up. Scam likely. I'm good. Okay. And then if we were to encode this, this would... What the hell? Stop. Phone. Stop. Seriously. Okay, so this would encode to 0, 0, 0, 0. A, right? 0, 0, 0, 0. S is 1, 1. S is 1, 1. I is 0, 0, 1. S is 1, 1. T is 0, 1. T is 0, 1. H is 1, 0, 0, 0. E is 0, 0, 1. S is 1, 1. T is 0, 1. U is Jojo. Wait, 1, 0, 1, 0. D is 1, 0, 0, 1. E is running out of room, 0, 0, 1. N is 1, 0, 1, 1. T is 0, 1. And S is 1, 1. So assist the students, no spaces, would turn into these zeros and ones. Okay. I think you forgot a O for I because it's the same encoding as E. Probably, yeah. Yeah. There. Okay. And so 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22, 23, 24, 25, 26, 27, 48 bits. So this whole thing compresses down to 48 bits, whereas if we did this in ASCII, it would be 8 times 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17. 8 times 17, which is 80, is 136. So originally it was 136 bits, and it compresses down to 48 bits. So it's about a 3-to-1 compression ratio. How does it know the difference between 00101 and 00101? It doesn't. But you can't have it cannot be ambiguous. I was waiting for somebody to ask that question. So good question, Mr. Wolf. It is impossible for there to be an ambiguous decoding. Because in order for there to be an ambiguous decoding, it would have to map to one of these intermediate nodes, and these intermediate nodes don't get any entries in it. Okay, so if you're asking to decode 00101, 001, that's a leaf node, that's E. Okay, there cannot be an encoding that is 00101 because that would be a tail, that'd be a child of E. E doesn't have any children. Only the leaves encode to anything. And so in order for it to be ambiguous, you would have to have like this, you'd have to have a non-leaf encode to something. So whenever you hit a leaf, when you're decoding, you're not going to have to do decoding, by the way. Whenever you hit a decoding, whenever you're decoding, you just go through this tree. When you hit a leaf, you output that character, get rid of the bits, and then move on to the next one. And it cannot be ambiguous. Because in order for it to be ambiguous, there would have to be a child of a leaf node. And leaf nodes, by definition, do not have children. So, whoever designed this was a very smart man. Was not me. When I learned this, I was like, damn, dude, damn. Because it's not only like, because I thought the same thing. I was like, how the hell do you not make this ambiguous? You know? But the thing is, like, it can't be. None of the interior nodes map to a letter. Right? That's why I did it as blank before. They don't map to anything. Only the leaves map to characters. In order for it to be ambiguous, you would have to have a leaf node that has a kid. And so he proved this, and he proved it was optimal. And he did this in, like, I don't know, a billion years ago. So, it's like 60s or 70s, something like that. He was a doctoral student at MIT. Yeah, 1952. 1952. 1952. Yeah. So 60, almost 60 years ago, he came up with this. Okay. So it's a given certain circumstances, it is optimal. It's not actually, because in reality, you're not compressing random letters. And so if you start looking at words and things like that, you can actually do better compression than Huffman coding, but for certain constraints, it's actually an optimal compression algorithm. And yeah, so here they've got the letter and the count, and then they build these intermediate nodes that are the sum of the counts, right? So X and P have a count of 1, this is 2, I and 2 count of 4, and so only the leaves actually map to a letter. And so E is going to, when you, at the end of the day, after you've built this whole tree, E is going to be 0, 0, 0. N is going to be 0, 0, 1, 0. And let's see. E is 0, 0, 0. N is 0, 0, 1, 0. And so you can see that the things that get used the most, because they come off the heap the last, they're towards the top of the tree. That's how the compression comes about. Because the things with the greatest count get popped off the heap at the very end, they're going to be very close to the root. And so they get less bits. Whereas things that get popped off first with the lowest count, they're going to be at the bottom of the tree and thus have the most bits assigned to them. So it is yeah. He was given a choice of a term paper or a final exam. And so he's like, I don't want to take an exam, and that's where that came about. That's funny. And he did better than his professor, who had been working with Shannon. That's amazing. He beat an MIT professor for a term paper. How do you like them apples? Huffman, unable to prove that any codes were the most efficient, was about to give up and start studying for the final. When he hit upon the idea of using a frequency-sorted binary tree and quickly proved his method the most efficient. So, fine, give me the final. No, wait. So, motivated by the desire to avoid a final, we have Huffman Coding. Yeah, and if I was his professor, I wouldn't even be mad. You know, it's like, well done. Because Shannon, if you guys don't know who Shannon, he invented Shannon theory, and basically the basis of all information theory, like compression and max. Like when you talk about how much bandwidth you have out of your Wi-Fi and your home internet, it's this guy, Shannon limits and things like that. So. Super smart dude, and so Huffman just in order to avoid doing a final exam beat Claude Shannon. Like that's that's like impressive. It's the kind of motivation. George Ansig was late to class and copied the formula thing from the board, thinking it was a homework and solved it. Yeah. All right, so that's it for today, guys. We'll pick this up on Wednesday if you have any questions about it, which I assume you will. The actual implementation details of it can be tricky, but I would like for you guys, partner up however you want. I'll make groups for this on Canvas, and you guys can just sign up for whatever group you want, and I'll let you guys sort out the groups, and I would start taking a crack at this. And what you're going to find is you're probably going to be like, wait, where do the pointers go? Like, I understand popping the smallest, but how do I actually do it? Now, like I said, you're going to need probably 3 different data structures. You're probably going to need the count, like what you did in part 1. You're going to need a priority queue that's going to be sorting the count and popping things off and pushing things on. And you're probably going to have the binary tree that's going to grow from the roots up. So maintaining 3 different data structures is like big brain time. So try to work it out. See if you can do one of these by hand, like I did right there. See if you do it by hand, right? And if you can get it to work on paper, then pretty good. But try to do that by hand first, and see if there's an example here on Wikipedia. Try encoding. This is an example of a Huffman tree. Let's try it. See if you get similar results. Remember, if there's ties, the ties don't matter. Look at me, I'm the professor now. Yeah, perfect. Yeah, remember, if there's ties, it doesn't matter whether they're left or right. It's the same thing. Okay. So work it out on paper, see if you get it, and try and have that ready to go by Wednesday. And I'll answer any subsequent questions you guys have then. If not, we're actually going to start learning Java. So I'm not going to be lecturing on this anymore unless you guys have questions. So come up with questions. Okay? So that's it for today, guys. Good luck. Gambate. Like I said, this is easily the hardest homework assignment that there is in this class. And yeah, we're going to be learning Java for the rest of this class. So this is kind of like your big final project. 3 data structures working in perfect harmony with each other. So this is typically a junior level assignment. So I'm giving you guys a junior level assignment as college freshmen. So Gambate. Yep. All right, that's it. Good luck, you guys. Peace out. Why not Python? Yeah, we could do that too if you want. We'll do Java and Python. See ya.